Welcome everyone to this fourth lecture of states of matter. So myself Varad Daoo, I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur. So in this class, we are going to see about the various types of gas laws. That is the Boyle's law, Charles' law, Avogadro's law. Right? Let me write this down. Lecture 4, states of matter. The first topic which we are going to study is gas. So we know that the volume of the gas depends upon the amount of gas, the pressure and temperature. That is, volume of the gas is a function of amount of gas, which is number of mole, the pressure and the temperature. From the from the study of behavior of gases, certain generalizations were made. These generalizations are called as gas laws, and these gas laws gives quantitative relationship between any two variables when the other two variables are kept constant. Right? So what are gas laws? So gas laws, these are laws. These gives quantitative relationship between any two variables when the other two are kept constant. Right? The first law which we are going to study is Boyle's law, also the called as pressure volume relationship. Right? So in 1662, Robert Boyle studied the changes in volume of a gas by varying pressure at a constant temperature of a fixed amount of gas. Right? So he used the J-type tube. Right? So the tube which he used, right, which was of this sort. So the experimental setup which he had used was like this. This was the experimental setup which he used, and this was filled with, let's say, up to this height. Let's say this is what, these are the two levels. This is the height edge, this is trapped air, right, and this is the mercury, and these are the J-shaped tubes which he used to, on which he carried out his experiments, right. So similarly, here filled up to more height, right, like this he changed the height of the or the amount of air, right. This is V dash of gas, this is V double dash gas of, is that V double dash gas less than V dash of gas, V of gas, right. This is H dash, this is H double dash, and this is mercury, right. So using this experimental setup, right, so in 1962, Robert Boyle studied the changes in volume of a gas by varying pressure at a constant temperature of fixed amount of gas. So he used this J-type um, shaped glass tube, right. He tapped some of the air in the tip of the tube, right. Here there was air, and measured the pressure exerted by gas by noting the difference in the height of the mercury column. The pressure of the gas is increased by adding more mercury to the tube, and the volume of the gas becomes smaller. In this way, Boyle studied the relationship between the pressure and volume of a given mass of gas at constant temperature. Right? So let us give the name to this figure. So this is Boyle's apparatus for studying relationship between pressure and volume at constant temperature. V double dash of gas less than V dash of gas, this is V gas. Right? So let us write the experimental setup. Experimental setup. So in 1662, Robert Boyle studied the changes in volume of gas by varying pressure at a constant temperature of fixed amount of gas. Right? He used J-shaped tube glasses as shown in the figure. Right? He trapped some air in the tip of the tube and measured the pressure exerted by noting the difference in height of the mercury in two arms of the tube, denoted by H. Right? The pressure of the gas is increased by adding more mercury to the tube, and volume of the gas becomes smaller. In this way, Robert Boyle studied the relationship between the pressure and volume of a given mass of a gas at constant temperature. Right? And the relationship which he obtained is known as Boyle's law. Is known as Boyle's law. Right? So the statement of Boyle's law is at constant temperature, pressure of a fixed amount of a gas varies inversely with the volume of the gas, right? And mathematically this can be written as, we can write as pressure is inversely proportional to volume, right? When N and T are constant. That means another way of writing this would also be volume is inversely proportional to pressure when N and T is constant. Right? Hence, what we can say, volume, if when we are changing the inequality to equality, we have to add a constant, right? That will be K by P, which implies P into V equal to some constant K, right? Where V is equals to volume of gas, P is the pressure of gas, and K is the proportionality constant, right? So the value of K depends upon the amount of gas and temperature, right? Value of K depends upon the amount of gas and temperature. Okay? And the value of K also depends on the units in which pressure and volume are expressed, right? So let us look at this statement. PV equal to K, which is nothing but constant. So what does this? So it means that at constant temperature, product of pressure and volume of a fixed amount of gas is constant, right? So this means that at constant temperature, product of pressure and volume of a fixed amount of gas constant. Now let us take a case. Let V1 be the volume of a given mass of gas at pressure P1 and at temperature T1. When the pressure is changed to, let's say, some value P2, right? At the same temperature, that means T2 is nothing but equal to T1. Then according to Boyle's law, we can write T1 V1 is nothing but P2 V2, which implies T1 by P2 is nothing but V1 by V2, right? Hence, what we can say, the Boyle's law may also be stated as the product of volume and pressure for a given mass of gas at constant temperature is constant. This means that if the volume of the gas is doubled, the pressure will be reduced to one half of this original value, and if volume is tripled, the pressure is lowered to one third. Right? What does this mean? So this means that if the volume of the gas is doubled, the pressure will be reduced to one half of its initial value, and if volume is tripled, then the pressure is lowered to one third, right? And so on, so on. So if you try to plot it on a diagram, what is the diagram? The graph is plotted between P and 1 by V, a straight line passing through the origin is obtained, right? Let us try to see the cross which we get. So the expression which we are going to use is P into V equals to constant. So this is the equation of an hyperbola, right? So hence the plots which we will obtain will be like this. It will be like this. So that, let's say, this is some P1 V1, and this will be some P2 V2, right? So this is isotherm, right? At some temperature T is equals to T1. Now if we want to plot for different pressures, what we can have is like this. So this is the origin. So then as we are going, what is going to happen is temperature is increasing. That means let's say this is at T3, then this is at T2, this is at T1. What does that mean? This means that T3 greater than T2 greater than T1, right? And this is nothing but pressure versus volume. Note that here what we have is pressure versus volume, right? So however, if we change this expression, let's say if instead of v, we plot 1 by v, then what we are going to get? This is the equation of a straight line, right? Y is equal to mx, right? Where x is 1 by v and slope is going to be the constant value, right? So if we plot like this, what we are going to obtain is this first, right? Pv is equals to constant. What does that mean? This means p is equals to constant by v. Then y is equals to m into x, where y is equals to pressure and x is going to be volume and m is nothing but slope, which is constant, right? Hence the slope is going to be straight line, right? Sorry, hence the nature of the graph is going to be straight line. This is pressure, this is origin, and now we are going to obtain straight lines. Oh, sorry. So here what we have on the y-axis, we have 1 by v, right? So as per this expression, it's going to be straight line passing through origin, right? Right. So hence, as we go, this is going to be T3, T3, T2, and T1. As we go down, what is going to happen is temperature is going to decrease. What does that mean? That means T3 greater than T2 greater than T1, right? The next plot will be PV, right? So PV is equals to constant, right? So if you plot it at different temperature, the plot is going to be a same, right? However, the value of the constant, as like we said, is going to depend on temperature, right? So we are going to plot how that is going to change. Right? This is 0, 0. This is PV versus free, and the expression PV is equals to constant, where constant is a function of temperature and n, right? So let's say we have like this, the next plot will be like this, and the next will be like this, right? So let's say this is at some temperature T3, this is T2, this is T1. And in that case, what is going to happen is T3 greater than T2 greater than T1, right? So it may be noted that Boyle's law is obeyed only by a hypothetical liquid, which is called as an ideal gas, right? At higher pressure and low temperature, the gases behave Boyle's law, right? So now let us understand the significance of Boyle's law. So the Boyle's law expresses in a quantitative manner the important experimental observation that the gases are compressible. When a given mass of gas is compressed by increasing the pressure, the same number of molecules occupy a smaller space. As a result, the gas becomes denser because mass per unit volume increases. For example, air at sea level is dense, but the density as well as pressure decreases with increase in altitude. For example, the atmospheric pressure at Mount Everest is only about 0.5 atmosphere. As a result, the oxygen in air becomes insufficient for normal breathing. This causes what is commonly known as altitude sickness. Right? Let us write this down. The Boyle's law expresses in a quantitative manner the important experimental observation that the gases are compressible. Right? When a given mass of gas is compressed by increasing the pressure, the same number of molecules occupy lesser space, right? Smaller space. As a result, what happens? The gas becomes denser because mass per unit volume increases, right? Let us move on to the next. Let's solve some examples. Question 1. A gas occupies 200 ml of water at a pressure of 0.82 or 0 bar at 20 degrees centigrade. How much volume it will occupy when it is subjected to external pressure of 1.025 bar at the same temperature. So what we are given? We are given P1 is equals to 0.820 bar. We are given V1 as 200 ml. We are given P2 as 1.025 bar, and we are asked to find what is V2. Right? So since temperature here we have 20 degrees centigrade, and here also we have 20 degrees centigrade. Temperature is constant. Therefore, applying Boyle's law, which is P1 V1 is nothing but P2 V2, which implies P2 is nothing but P1 V1 by P2, which is 0.820 bar multiplied by 200 ml divided by 1.025 bar. Therefore, V2 is going to be 160 ml. So let us move on to the next topic, which is Charles' law, also known as volume temperature relationship. Right? It is known as volume temperature relationship. Right? Right? So in 1787, a French scientist Jacques Charles studied the effect of temperature on the volume of gas at constant temperature, and the studies were examined by Gay-Lussac in 1802. The following general observation about the relationship between the pressure and volume of a gas was observed, which is known as Charles' law. Right? This one is written by 1787 French scientist Charles. Right? And as per this law states that at constant pressure, the volume of a given mass of a gas, the volume of a given mass of gas increases or decreases by 1 by 273 of its volume at 0 degree centigrade for each 1 degree rise or fall in temperature. So mathematically we can say that, right? So let us say, so let V0 be the volume of a given mass of a gas at 0 degree centigrade, and Vt be the volume, Vt be its volume at any temperature T degree centigrade. Right? Then the volume Vt can be written as for 1 degree rise in temperature, for 1 degree rise in temperature, Vt is going to be V0 multiplied by 1 by 273. For T degree rise in temperature, it's going to be Vt is going to be V0 multiplied by 1 by 273 multiplied by T. Right? Hence, volume at T degree centigrade is going to be initial volume plus increasing volume, right? So Vt is going to be V0 plus V0 multiplied by 1 by 273 multiplied by T, which implies Vt is going to be V0 into 1 plus 2 by 273, right? This is going to be increase, right? In case of decrease, what we will be getting is Vt is equals to V0 into 1 minus T by 273, right? This is decrease in volume. Right? So these are the two definitions of Charles law, right? So the next subtopic in this is absolute or Kelvin temperature scale, right? So when a graph is plotted at constant pressure between the volume, which is along y-axis, and temperature along x-axis, a straight line is obtained, right? When this line is extrapolated to lower temperature, it represents zero volume, right? So the plot which we will be obtaining is this one, right? So this is going to be Vg, this is going to be volume, and this is going to be the temperature, right? So when we plot this line, what we get is, so we get 1 point here, 1 point here, 1 point here, right? This is going to be temperature, right? So when we plot this line, what we get is, we get a graph like this. Okay, and when we extrapolate this graph, use a different color. When we plot, extrapolate this graph, what we get is, this point we get as minus 273, right? So this is in degree centigrade, right? So this is the point at which it is going to cause on the negative temperature axis, right? And the points are going to be like this, right? Hence, this temperature is what we call as, so we defined a new scale, which is different from which is different from temperature, right? Which is different from Celsius scale, and we call it as a Kelvin, Kelvin scale of temperature. And the conversion between is going to be temperature in Kelvin. Temperature in Kelvin is going to be temperature in degree centigrade plus 273.15, right? And this is called as thermodynamic scale of temperature, right? Kelvin scale, Kelvin temperature scale is also called as thermodynamic scale. Kelvin temperature scale is also called as thermodynamic temperature scale. So as per this, what we have is, volume is directly proportional to temperature. That means volume or temperature is going to be constant, or volume is nothing but some constant multiplied by temperature, right? So hence, when we plot the graphs, the nature of the graphs is going to be like this. This is 0. So here we have volume, and here we have temperature, right? Let's say, so what we are going to have is, we are going to have plots like this. So these are all the points which are going to converge onto a single point, right? So if you go like this, if you go like this, these are all going to be converging at a single point, because this is temperature in degree centigrade. So this is going to be 273 Kelvin, right? And these are all isobars. So these are plotted at particular temperature, right? A particular pressure, right? Let's say this is P2, this is P1, this is P3. Then the order is going to be P1 less than P2 less than P3. Right? So practical significance of Charles law. So one of the interesting applications of Charles law is the use of hot air balloons in sports and for meteorological observations. According to Charles law, gas expands on heating. Since the mass of the gas sample is constant, the larger the volume at higher temperature will have lower mass per unit volume and therefore lower density. Thus, hot air is less dense than cool air. This causes a hot air balloon to rise by displacing cool air. On this principle, hydrogen balloons were also developed as a means of transportation across the Atlantic, right? So, application is hot air balloons. Hot air balloons, hydrogen balloons, right? Let's try to answer solve some question, right? Sample of gas occupies 1.5 liter at 25 degrees centigrade. If the temperature is raised to 60 degrees centigrade, then what is the new volume of the gas if pressure remains constant? So what we are given is, we are given V1 as 1.5 liter, temperature has been given to us 25 Kelvin, 25 degrees centigrade, that is nothing but 273 plus 25, which is 298 Kelvin. T2 we have been given as 60 degrees centigrade, which implies T2 is 60 plus 273, which is nothing but 333 Kelvin. Okay, 273 plus 60. And we are asked to find what is V2. So we straight away use the Charles law, right? V1 by T1 is equals to V2 by T2, implies V2 is V1 into T2 by T1. So V1 is going to be 1.5 multiplied by 333 divided by 298, which implies V1 is going to be 1.68 liter, right? So this is going to be answer. So in summary, in this class, what we have seen is, we have seen Boyle's law, its application of Boyle's law, association to Charles law, application of Charles law. Right? We have also solved some examples. So in the next class, we are going to see about Gay-Lussac's law, that is the pressure temperature relationship, and Avogadro's law, that is nothing but volume versus number of moles relationship. And then we are going to combine all this relationship and generate an equation which is called as an ideal gas, right? So I thank you all for attending this class, and I hope to see you again in the next class. Thank you.